right, we are going to look at vectors. So, what is a vector? So, a vector is a quantity that has both magnitude, which just means size, and direction. So it could be represented using a directed line segment where P is the initial point or the tail, and Q is the terminal point or the tip. Vectors are denoted by using the arrow symbol or array. So in this picture we have PQ. We can name it as PQ or vector P. And we probably wouldn't write it bold, but having a bold letter means a vector. So given a vector with an initial point, x1, y1, so just a generic point, and terminal point, x2, y2, again, just another generic point, the magnitude of the vector, which is labeled like this, magnitude, can be found by using the distance formula. So the magnitude of V is the distance formula, which is just the difference in the x's squared plus the differences in the y's squared, all of that square root. So let's look at some. I'll just look at, honestly, I'll just pick two of them. So AB is here and here. So the magnitude of AB is the difference in the x's squared and the difference in the y's squared. So 8 and -7, that is a difference of 15. And -4 to -2, that's a distance of 2. So 225 and 4. So the square root of 229, and that's about 15.13, but either one of these is okay. Let's look at another one. So the magnitude of EF, and it's a double line because having one line means absolute value. This double line is meaning magnitude. So the difference in the x's squared plus the difference in the y's squared. So I'm looking at -1 to -6. So that's a distance of 5. And then -5 to 7, that's a distance of 2. So 25 and 4. So the square root of 29, which is about 5.39. All right. Now we have something called the zero vector, and I'm hoping that you can make some inferences about what that means. That is just a vector with a magnitude of 0. And then we have some different types of vectors. We could have parallel vectors, so same or opposite direction, but not necessarily the same magnitude. So I could have vector A, and I could have vector B, where A is parallel to B. Same magnitude and direction, so I could have vector M and vector N. So that just means M equals N. and opposite vectors. So they have the same magnitude, but they're opposite directions. So I could have vector u and vector v. So we could say that u is negative v. All right, so let's kind of look at some examples. We're going to look at A and E first. I'm going to circle them and see what they are. So A and E. They look to be the same magnitude, and they're in opposite directions, so I would consider these to be opposite. I and F, they look to be the same magnitude and the same direction, so they're equal. D and E, I think they're parallel because they're not the same size. They are going parallel. All right, clear these out to do the next. B and G, well, they're not going opposite directions. They're not parallel. So this will actually be none. And last set, C and H. Let's see, they look to be about the same size and are going opposite directions, so they are opposite. All right, let's look at proving that they are the same. So you can show that two vectors are equivalent if they have the same magnitude, so the same distance, and the same direction, and we would use the slope formula. So let's see, we have AB and CD. So let's do the magnitude of them. So AB, it's a square root, difference in the x's, difference in the y's. It's -6 to -2, it's a distance of 4. -7 to 3, that's a distance of 10. So 4 and 4 is 16, 10 and 10 is 100. So the square root of 116, we'll leave that because we'll do CD now. So the difference in these 2 and 6 is 4. The difference in -10 and 0 is also 10. So I don't even have to do the math because I started off with the same distances. So okay, we have the same magnitude so far. Now we want to know the same direction. So I need to find the slopes. I'll do that in a different color. So slope for AB is the change in y, so -7 minus 3 over the change in x, -6 minus -2. So that gives me -10 over -4, which reduces to 5/2. Well, the slope for CD, let's see, it's 2 minus 6. Oh, I guess I should do my y's first, like I should. -10 over, oh my gosh, 0, and 2 minus 6, so -10 over -4, which reduces to be the same. So these are equivalent because they're the same. So if one of these measures is not the same, then they are not equivalent. All right, so I'll let that one be one for you to try on your own. All right, standard position of a vector. So standard position is when the initial point of a vector is at the origin. All right, if a vector is in standard position with the terminal point AB, then the component form of V is V equals, and we use these like I don't want to call them inequalities, but inequality symbols. So the magnitude and direction angle theta of a given vector in component form can be found using this. So we know the magnitude of V is going to be the distance in the points. So if we have point A and point B, A is the X, B is the Y, and we have that original origin. So you'd have A minus 0 squared, so A squared. And then you have B minus 0 squared, so B squared. And then the direction angle theta would be found by doing tangent theta is B over A. Now these should look familiar, right? So let's just do a couple of these. Okay, so R equals 7 and 24. So the magnitude of R is 7 squared plus 24 squared. And then the square root of all of that. So 49 plus, I think that's, gosh, I want to say that's 576, but I don't know. 24 times 24 is 576. So plus 49 is 625, which actually is a perfect square itself, so 25. And then to find the direction angle, it's B over A. So what I'll do is be in degree mode in my calculator. I'm going to do the inverse tangent. So inverse tangent of 24 over 7. And so that's going to give me a theta of 73.74 degrees. Okay. Let's look at another one. Let's look at 4. So the magnitude of K is, let's see, negative 11 squared plus 6 squared. So 121 plus 36. Ooh, not a nice number. Square root of 157, which we can get the decimal. It's approximately 12.53. And then tangent theta is 6 over negative 11. So, inverse tangent of 6 over negative 11. Which in my calculator gives me negative 28.6. But if I think about where this vector is, negative 11.6, we are up here. So the negative 28 tells me I'm somewhere here-ish, going this way. I need to be up here. So what I can do is I can add 180. Oops. Adding 180 will put me in the quadrant I need. So adding 180 gives me 151.39 degrees, which is where we need to be. All right. Let's look at some more stuff with vectors. So if we want to write any vector, so any vector with initial point x1, y1 and terminal point x2, y2, we can write it in its component form like this. V equals, so component form is that inequality looking notation. The difference, in the x values, comma, the difference in the y values. So, I'm gonna look here, CD, where C is here and D is here. If I were to write it in its component form, we can do 6 minus 3, comma, 3 minus 5. So I get 3, negative 2. I wonder, can we graph that? What would that look like? 1, 2, 3. 1, 2, 3, 4, 5. And D is 6, 3. 3, 4, 5, 6. 1, 2, 3. D. Maybe I don't like that. So, oh, hang on. Let's put those points back. So having those 2 points from C to D would make a vector in standard position 3, -2 is what it would look like. All right, let's do this one too. So we have -2 minus 5 and 1 minus 10. So we get -7, -9. All right, let's look at some of these. So give the component form, the magnitude, and the direction angle. So the component form, let's do that first. So that's going to be 4 minus 2 and 1 minus -9, which really becomes +9. So component form is 2, 10. The magnitude of MN is the difference in the x's, so 2 squared, plus the difference in the y's, which is 10 squared. So what is that going to give me? 104. So the magnitude is the square root of 104, which is about 10.2. The direction angle, remember, is the tangent theta equals b over a. So tangent theta is 10 over 2. So let's see, when I do inverse tangent, 10 over 2 is just 5. So inverse tangent of 5, it's going to give me 78.69. And we can check to make sure I don't have to add or subtract the 180, because 210 would put us in quadrant 1. So 78 is going to be in quadrant 1 as well. So we are good there. Okay. Ooh, let's look at one where if we're given a graph. So, all right, the 2 points are 1, 2, 3, 4, 1. That's the second point because that's where the arrow is going. So the initial point is -1 and 1, 2, 3, 4. All right, so component-wise, we have 4 minus -1 and 1 minus 4. So I get 5, -3. The magnitude, we'll call it C, is 5 squared plus -3 squared. So 25 and 9, which gives 34, which gives about 5.83. And then the direction angle, so tangent of -3/5. So let's see, inverse tangent of -3 over 5. It gives me a negative angle. So let's see where we're at. So directional wise, we're 5, -3, so we're somewhere here. So the negative angle it gave me is -30.96. So I need to find I need to be in this quadrant anyway, but I don't really want a negative angle, so I need to add 360. So if I add 360, I get 329.04. All right, more with equivalent Vectors are equivalent if and only if they have the same component form. So let's see. Component form for A, B, we're going from A to B, would be -7 minus -3. -2 minus 6. So that gives me -4, -8. So that's AB. We'll do CD. So that's -1 minus 3, which gives -4. And -9 minus -1, which gives -8. So these are equivalent. Let's look here at this one. So AB. Let's see, 0 minus -9 is 9. -8 minus -2 is -6. 4 minus -5 is 9. 8 minus 2 is +6. These are not the same, so not equivalent. Okay. We can do some operations with vectors. We can multiply it by a scalar. So all that means is we can multiply a number. So it's going to change the magnitude of the vector. If k being just some number we multiply by, is negative, the vector will reverse and go the opposite direction. So here's one vector. If we multiply it by 2, we're getting larger. If we multiply it by 1/2, getting smaller. And if we multiply it by a negative, it changes the direction. Okay, we can add vectors. So if we were to look at V and W, so here's one vector, here's another vector. Let's see, the vectors are positioned so that the tip of V coincides with the tail of W. The sum, V plus W, is called the resultant, and it extends from the tail of V to the tip of W. We can also subtract them. So the difference of two vectors is defined as, so V minus W is the same thing as V plus -W. All right, here's some rules. So if we have a vector V being A1, B1, and W being A2, B2, with K being a real number, if we're going to multiply it, we're going to multiply everything. So we're going to do K times A1 and K times B1. So we'd multiply both components. The addition, we would add our X components, and we would add the Y components. Subtracting them is doing the same thing. So we just subtract the components. All right, so let's look. Find each of the following. So we'll do all four of these. 2C, well, C is -4, 5. And doing 2 is multiplying, essentially like distributing. So it's going to become -8, 10. A plus B, so -6, 2, and 1, 7. If we add them, -6 plus 1 is -5, and 2 plus 7 is 9. Subtracting them, so C is -4, 5, B is 1, 7. We can subtract the components. So -4 minus 1 is -5. 5 minus 7 is -2. Let's do A minus 3C. So A is -6, 2. And I'll just go ahead and throw in the 3C. So that's going to be -12 and 15. So -6 minus -12 would really be adding 12. So 6. And 2 minus 15 is negative 13. Okay. I'll leave those two examples for you to do. All right, unit vectors. So a vector with a magnitude of 1 is called the unit vector. Given any non-zero vector v, a unit vector u in the same direction of v can be written like this. So u equals 1 over the magnitude of v times v. So let's look at an example. So find a unit vector with the same direction as the given one. So I need to find the magnitude of v first. So that's the square root of the component squared. So negative 5 squared plus 12 squared is going to give 25 plus 144, which is the square root of 169, which is a perfect square of 13. So then u equals 1 over 13 times v. Well, v is negative 5, 12. So u equals negative 5 over 13 and 12 over 13, because I'm just multiplying. All right, let's look at another one. I'll do 10. So let's see here. Gotta find the magnitude first. So 16 squared plus negative 8 squared. 256 plus 64. That's gonna be 320. Let's see. Let's try and reduce that. So that would be 32 and 10. Neither of those are perfect squares. 32 is 16 and 2. 10 is 2 and 5. So 16 is a perfect square. So I'm pull it out as 4. And there's a pair of 2's. So I can pull that out as a pair of 2's. And then I'm left with 5. So really, that becomes 8 root 5. Okay. Pause if you need to, because I'm going to erase the scratch work. Okay. So now, u is 1 over that magnitude times the vector itself. So 16 and negative 8. Okay, let's multiply that. So let's see. And I'm going to do some side work over here. So 1 over 8 root 5 times 16. Well, 16 and 8 will cancel out to just be 2. So I have 2 over root 5, but we want to rationalize that. So times both the numerator and the denominator by root 5, and we get 2 root 5 over 5. Now I'm going to do the same thing with the other one. So 1 over 8 root 5 times negative 8. Well, 8 and 8 cancel out to be 1, so I'm left with negative 1 over root 5, but I need to rationalize. So I get negative root 5 over 5. Oops, drop a pen. Okay. Okay. Now before I get into this part here, one thing I want to add, only because it shows up in the Pearson work, is, let's see. It might ask you to write a vector in the form AI plus BJ. So I'm going to use some different points here. Instead of these two, I'm going to use 0, 0, and 2, 4. So what we want to do here is we would say in the component form, I don't want to say component form, but in this form here, we would say it would be x2 minus x1i plus y2 minus y1j. So the difference in the x's is going to be 2 minus 0 and then that gives us just 2. And then the difference in the y's is 4 minus 0, which gives just 4, minus 0. So we get, oh, it's literally just, sorry, I'm stepping through the homework as I'm doing this, 2i plus 4j. 2i plus 4j. Yep. All right. It works the same if the point, like I could do it off of this one. I could say, all right, 8 minus negative 1i plus negative 2 minus 4j. So it'd be 9i plus, well, it'd be plus negative 6, so minus 6j. All right. Now let's look at everybody's favorite word problems and with these bearings. Okay. So a quadrant bearing is the acute angle between a vector and the north-south line, or the y-axis. The vector to the right is 60 degrees east of south and is written as this. A true bearing is the angle measured clockwise from the north vector. A true bearing of the vector to the right is 120. True bearings are written with 3 digits. So a true bearing of 15 is written as 0, 1, 5. So that 120 is going to be this part here. All right, for each vector, give the quadrant bearing and the true bearing. Okay, so the quadrant bearing is going to be this angle right here. So that is going to be 5 degrees. And let's see, what would that give? We are, let me try and figure out, the vector to the right is 60 degrees east of the south. So this is 5 degrees east of the north. So east of the north. The true bearing is measured clockwise from the north to the vector. So that actually happens to be the same. So 0, 0, 5 degrees. Okay, so the whole angle is 212. The quadrant bearing is the acute angle between the vector and a north-south line, or the y-axis. So this angle right here. So let's see. We would get from here all the way to here would be 270. So 270 minus the 212 is 58. So 58, but I'm going this way. So that direction's west, so 58 degrees west. And then I'm using the south, so it's west of south. And then the true bearing is the clockwise. Let me erase what I have. Clockwise from the north to the vector. So clockwise is this way, and then to the north of the vector. So I think that angle. So hang on. And I'm incorrect. Clockwise from the north to the vector. So I need to go this way. So that's 180 plus 58 to give 238. All right, let's look at some word problems. Let's see here. All right, an airplane is flying at a bearing of 245 degrees at 550 miles per hour. Give the velocity of the airplane as a vector in component form. So, flying at a bearing of 245. So where is 245? Okay, so a bearing is from the north all the way to the vector, clockwise. So north, clockwise, 245. Well, that's 90. That's 180. This is 270. So 245 is somewhere here. 245. So that whole thing, 245. At 550 miles per hour. Okay, I had to phone a friend real quick. So let me start all over with this problem. Okay, so an airplane is flying at a bearing of 245. So my drawing is not incorrect. Of 245 going 550 miles per hour. Give the velocity as a component. So what we can do here, our x component is going to be cosine of an angle. The y component is going to be the sine of some angle. The 550 miles per hour is going to be our, oh, and I wrote 550, that's going to be like our R value, if you want to think of it as R cosine theta, R sine theta. We just got to figure out what angle we're going to use, because we're not going to use 245 because that's going in the negative direction. So what I want to do is I want to find what is it from the positive direction. What is this angle here? So I know that quadrant 1 is 90, quadrant 2 is another 90. So far this piece right here is 180. And I have to figure out what this little chunk right here is. So what I can do is I can do some side math and look at this angle here is going to be 270. Well, I have 240 here. So if I do 270 minus the 245, that'll give me that little chunk here. So 270 minus 245. So that tiny little chunk right there is 25. So what I can do to get my angle I need for here is do the 180 plus 25, which is going to give me 205. And then I can throw these in a calculator. And 550 times cosine of 205 is negative 458.47, and 550. Sine of 205 is negative 232.44. All right. Let's look at another one. A man pushes a lawnmower with a force of 25 pounds uphill at an angle of 40 degrees. So uphill at an angle of 40 degrees. Give the force exerted on the lawnmower as a vector in component form. So again, that's going to be like a r cosine theta, r sine theta kind of deal here. So the force is that 25 pounds. So we're going to do 25. And then this angle is already given to us in what we need. So cosine 40 and 25 sine 40. So if I put it in a calculator, I get 19.15 and 16.07. All right. Let's look at one last piece here, and I'll just do one problem here. So a vector can be resolved into a horizontal component and a vertical component. And both those components are in x and y, so they're the rectangular components. So because the rectangular components form a right triangle, we can use trig to find them. So Danica is pulling a sled with a force of 400 newtons using a string. If the string makes a 35-degree angle with the ground, so 400 newtons of force, 35-degree angle with the ground, find the magnitude of the horizontal and vertical. So let's see, to find, this is the y, this is the x. The x component would be adjacent and hypotenuse, so that's cosine. So cosine of 35 is going to equal x over 400. So x is going to equal 400 cosine 35. So let's see what this gives. So cosine 35 times 400 gives me 327.66. Sine is the other one. So sine of 35 is y over 400. So y is 400. Whoa. Sine of 35. So 400 sine of 35 is 229.43. And there we have it.